Hi guys, welcome to another video on the basic concepts of organic chemistry. In a delocalized system where the electrons are delocalized and they are not restricted to between two atoms only, the orbitals overlap to form new orbitals, which we call the molecular orbitals. So it's very important to know how to draw the molecular orbitals in a correct way. So in this video we will learn how to draw molecular orbitals, but before that I'll try to introduce what molecular orbitals mean. So molecular orbitals are formed by the linear combination of atomic orbitals, and you have to remember that the number of molecular orbitals formed are always equal to the number of atomic orbitals that combine to form those molecular orbitals. Now, during this formation of molecular orbitals, the wave functions of these orbitals or electrons, they overlap or combine or interfere either constructively or destructively. You might know about constructive and destructive interference. So where there is constructive interference, the amplitude of the wave increases, and that is a region of the maximum probability of finding electrons. And when the crust combines or overlaps or interferes with the crust, then we say it's a destructive interference, and that is where the probability of finding electron is minimum. And the regions where the probability of finding electron is minimum is known as the nodes. So during the formation of these molecular orbitals, there are certain regions where you have to place nodes or nodal planes. Now you have to learn how to draw molecular orbitals, where and how many nodes to place in a particular molecular orbitals, and what would be the wave functions, the orientation of the wave functions of different atomic orbitals present in a particular molecular orbital. So we'll explain this with the help of an example that is of 1,3-butadiene. So 1,3-butadiene, we have already discussed this in another video that you can find here in the link. It's a conjugated diene system in which these pi electrons are delocalized over the whole system or all of the 4 carbon atoms, and so a neutral 1,3-butadiene goes to form a charge separated structure, which is of course unstable, and it goes back. The electrons are delocalized again to form this neutral structure. So we can draw 1,3-butadiene in this form, in which you can see the dotted line shows that the electron density is spread over the whole molecule or all the 4 carbon atoms. So we will learn how to draw the molecular orbitals of 1,3-butadiene, how many molecular orbitals can be formed, and where and how many nodes you have to place in a particular molecular orbital. So we will explain this on an energy scale. So the first molecular orbital that 1,3-butadiene can have is here. So you have 1, 2, 3, 4 carbon atoms with their corresponding p orbitals, which combine to form these pi bonds, and because of resonance they can overlap with each other to share electron density or to spread the electron density throughout the whole system. Now to draw the molecular orbitals, or to know what would be the wave functions of these atomic orbitals in a particular molecular orbital, or where you need to place a node or is there any node present in this molecular orbital, first you need to know that we consider this electron density as a sine wave. It's a sinusoidal wave, and we will explain this with the help of quantum mechanics. We will not go into the details of quantum mechanics, but it is mathematically explained through quantum mechanics. So we consider this as a sine wave, and it is considered to start at one bond length away from the first carbon. Like this wave starts from here and it ends at a point one bond distance away from the last carbon. And this is applicable to all the systems. Like if you have 135 hexatriene, you can do it the same way. So for this 1,3-butadiene, we have 4 carbon atoms, and in between these 4 carbon atoms we have 1, 2, 3 bonds. But this sine wave or sinusoidal wave starts at one bond distance away from the first carbon, and it ends at one bond distance away from the last carbon. So we have a total of 1, 2, 3, 4 and 5 bond distance available for this sinusoidal wave. So to draw the wave in the first molecular orbital, where we have 5 bond distances, so this is the first orbital, so we divide 5 by 1, which is equal to 5. Now this resultant 5 means that the crest or the trough of this sine wave in the first molecular orbital would cover a distance of 5 bond lengths. So this sine wave starts from here and it covers a distance of 5 bond lengths to meet this sigma framework again at this point. And so you can see that throughout this whole molecule, the amplitude of this wave is positive. And where the amplitude is positive, or even if it is negative towards the lower side, there the probability of finding electron is maximum. If the amplitude is 0, like if the wave somehow falls down to this sigma bond and the amplitude is 0, then we say that the probability of finding electron in that region is minimum. But in this case, you see this wave starts from here and it ends here. So throughout this whole system, the amplitude of the wave is positive, which means that electrons could be found here. And so, which means that in the first molecular orbital of 1,3-butadiene, electron density can be shared easily, or it could be spread easily from the first carbon till the last carbon. And that, in other words, mean that these orbitals can effectively overlap with each other. And you already know that for two orbitals to overlap, the signs of their wave functions must be similar, or in this case, one lobe is shaded and the other is unshaded. So if you have two shaded lobes on the same side, they can overlap, or if you have the unshaded part on the same side, then they can overlap. So if the wave functions or the sine wave has a positive amplitude throughout the system, that means that electrons could be easily spread, or electron density could be spread throughout the system, and that means that these orbitals can overlap. And there are 4 orbitals which can overlap effectively, and that means that all of them must have the same wave function, either above or below this sigma framework. So we can draw the orbitals in this way so that the wave functions are similar. And another important information that you get from this is that there is no node formed or placed in this molecular orbital. Now we move on to the next higher energy orbital. Now I have drawn these orbitals with the same wave functions as this, but we will see at the end what could be the actual position after drawing the sine wave. So this is the second orbital, molecular orbital, and again we have 1, 2, 3, 4, 5 bond distance available for the sine wave. So in this case we divide 5 by 2, which is equal to 2.5, which means that this sine wave starts from this point at one bond distance away from the first carbon, and it will cover a distance of about 2.5 bond lengths to meet this sigma framework, and then it will go down. So it starts from here and it covers a distance of 1, 2 and 2.5 bond distance to meet this sigma framework here, and then from here it goes down to cover another 1.5, 1.5 and 2.5 bond distance to meet at this point, that is 1 bond distance away from the last carbon. So the amplitude, so the wavelength of this wave is half of the first one, right? And so you can see it starts from here, the amplitude is positive, and it meets the sigma framework here, which means here the amplitude is 0, and then it goes down maximum amplitude and then fades out again to meet this sigma framework. Here the amplitude is 0. Now we have a point where the amplitude is 0, so it means we have a node here. And so you can put a node here, and you already know that when there is a node or a nodal plane, the wave functions of the two orbitals on either side of this node must have opposite wave functions. So the wave functions are opposite. You can see this is a shaded part up here, so the unshaded part should be up and the shaded part should be down on this side. And because there is no node in between these orbitals, they have the same wave functions on both the sides. Remember, the sizes of these orbitals are not the same. I have drawn these with different sizes to touch the amplitude of the wave, and you can draw them in the correct size here to touch the wave as well, right? And actually this amplitude is the probability of finding electron, and orbitals mean the same, so you can draw them in the correct way. So here we have two orbitals with the shaded part, the lobe up, and here we have the two orbitals with the shaded lobes down here, and we have one node or nodal plane right in the center of the two carbon atoms. For the third orbital, again we have a 5 bond distance available for the sine wave. So in this case we divide it by 3, which is equal to 1.66, and so the wave starts from here, covers a distance of 1.66 bond length, meeting it here, and then it goes down covering a distance of 1.66 bond length again, it meets here, and then it goes up, and after 1.66 bond length it goes here. And now you see that it meets twice at this sigma bond, so which means that amplitude is 0 at 2 points. So we have two nodes, and across the nodes the lobes must have opposite wave functions. So actual position is this. So we have two nodes, and across the node the wave functions must be opposite. Here we do not have any node, so the wave functions are similar. Finally, in the last orbital, again we have 5 bond lengths available for the sine wave, and in this case we divide it by 4, which is equal to 1.25. So the wave starts from here and it covers 1.25 bond distance, then it goes down and it meets here at 0.5 bond length after 1.25 covering a distance of 1.25 bond length. Then it goes up and it meets here, and then goes down and it meets here. So the final situation is this, because it meets the sigma bond at 3 positions, or the amplitude is 0 at 3 positions. So we have 3 nodes here, and across the nodes the wave functions must be opposite. So we have a total of 4 molecular orbitals possible for 1,3-butadiene, and this is how you can draw them in the correct way with the correct wave functions or signs of wave functions and the correct number and position of the nodes. You might see in books that these nodes are drawn at the center of the bond. They're not actually at the center of the bond. They are somewhat at towards the right or to the left, depending upon what bond distance it covers, but you can draw it at the center just for simplicity. So finally we can draw the molecular orbitals in this way. The first one has similar lobes on or wave functions on either side, so they can effectively overlap. The electron density is available to all the orbitals, and they can easily overlap. The resonance or delocalization is more effective here. And then we have the second molecular orbital, in which we have a node right in the center. So these two can overlap, these two can overlap, and no overlap is possible here. Then in the third we have 2 nodes, and so you can see the overlap is possible only here. No overlap is possible with these 2 orbitals. Finally we have this, in which there are 3 nodes, and so the wave functions are opposite for all the orbitals. So this is how you can draw the molecular orbitals of 1,3-butadiene. And because we can have 4 molecular orbitals. The first two, the psi1 and the psi2, are the bonding molecular orbitals, and psi3 and psi4 are the anti-bonding molecular orbitals. And you can place the electrons which are involved in delocalization. So we have two double bonds, and each double bond has two electrons, or a total of 4 electrons are present or involved in delocalization here. So starting from the lowest energy orbital, you fill the first one with 2 electrons, and then you fill the second one with 2 electrons, and the third and the fourth are empty. So this is how you can draw molecular orbitals for 1,3-butadiene, and you can follow the same procedure to draw molecular orbitals for all the other molecules or ionic species which involve delocalized electrons or orbitals in different ways. Right, so I hope it helps. So thank you so much for watching. Stay tuned for more lectures in basic concepts.